to... That's weird. I set this to 24 frames per second. Why has it gone to... Let me just... let me change my settings again. Video settings. 24. Oh, I set it at 24. So what the heck? Right, I was trying to make sure. So yeah, I'm just having some issues with the settings here. It says 29 frames per second. What the hell? Anyway. Alright, so I've been working on the ideas on making a magnet motor more efficient. Well, initially when I was designing the segments, so I'm going to simplify it by just doing one row. So we have a row of magnets, and there's a gap of about 1 millimetre to 2 millimeters in between each one. You got to keep the spacing. You got to keep the spacing quite small, otherwise you end up with flux, too much flux straying out. And so Magnetron was asking me. He said he doesn't understand it. Well, I'll try and explain it simply. Now, normally when you've got an array of magnets in a line and you're using an actuator of a bias, we have another magnetic, say we have a rod coming down, and let's say that steel rod is being biased with a south pole, so it's actually coming down here. We have south coming out the end of this piece of metal, and what you get is if this end is south, then we have north, and then we have south, and then we have north, and then we have south, north, south, so on, so on. I'm just drawing it in so you can oops, yeah, that's right. So what normally happens is when you get to the end, you have the south pole. So this thing is moving. This is the polarity of the flux, and this is the direction of our rod moving along, right? So this rod doesn't want to be adjacent to south because it's been propelled in towards the north. It gets to the north field and then it realizes that there's another south field there, and it gets propelled to the next north field, and then so on and so on and so on. But when you get to the end of the array, you have the problem of cogging, because now you have a south field attracted to the north field at the end, because there's no longer any more south field to expel it further. But you need a short array. The array's got to be fairly short, because if it's not, the distance between this end and that end, if it's too great, you don't get the propulsion that you want in the biased steel rod. So one way of overcoming that, and I've explained it so many times, I've lost count, but if we get these magnets, right, I'm just going to try and show you. I need to get this open, just give me a sec. That was pretty tight. Just give me a sec, I'm just getting some bits of steel out of here, because this explains it the best way. Right, when you have a piece of steel on a particular pole, it seems it's quite happy there. It's quite happy, but you introduce, come on, steel. Maybe I should use the other end actually. Them ceramic ones are a bit unpredictable. It's quite happy, but if you introduce more than 2 or 3, if I put another one there and you push it towards the other steel, it actually, maybe it's because it's longer, I don't know. Come up, you bugger. What happens when you introduce 2 the same length, let's say? You get them repelling each other. Right, I bet you see it wants to lay down. They want to repel each other, so I push that one up and that one is pushed away. Now we can use that. So instead of reducing the biasing on the end of the array by subtracting the north field, which is what you could do by using a south field. So if we had a different orientation of magnet that was, say, below this, and it was facing sort of towards the magnets in this direction, so that this was so if you put south at the top, right, you would subtract the north field. But the trouble with doing it this way is, well, you can guess, it reduces the amount of propulsion that you get on the iron that's been attracted to the north, because when it gets to the end here, it's basically going to be weak, and you no longer have the thrust that you want to maintain. So how can you overcome that? Well, instead of having south at this end that subtracts that north, what you need to do is have another north. And you think, that's going to make it even stronger. Well, yeah, of course it will. But you have multiple norths, right? So this is south down here, and this is pointing away from it somewhere in the ether that you don't want. Now, what happens if you have another magnet pointing in the other direction? You have multiple magnets actually, and this is also north, and now south pointing somewhere into the ether. What you've got now is you've got 3 norths all at this end, and it amplifies the amount of torque that you get for your piece of steel that's moving along this array. But when it gets to this end, it's suddenly confronted with a dilemma, because all of a sudden you've got 3 north poles and they all reject each other. North doesn't like north, and it's certainly not going to like 3 north for poles. So what you end up with is ejection instead of attraction at that very point, but you have good attraction in coming to the end. So this is the reason. Oh, I've dropped that bit of steel now. This is the reason why I was testing some ideas with this magnet in the bottom down here. So this magnet down here is the same. Let me see if I can get it better focused. Oh, let's see, where's my pointy thing going? This is the reason why this magnet at the bottom down here is the same pole as the end of these magnets, because we have effectively a north field, a north field, and a north field pointing from down below, so that when the piece of steel, ferrite or whatever you want to use, using a bit of ferrite, so when that comes along this row, it's gonna, oh shit, I didn't want that to happen. Hang on a minute. Hang on. Just a minute. That teaches me for putting my big magnets near that thing. Hang on a sec. I'll just get that big magnet out of the way a minute. Sorry. So, now we have a situation where this magnet that's biased, sorry, this ferrite that's biased with magnets of a particular pole, it's going to suddenly jump from, obviously I haven't built in another magnet on the entry point yet, because I haven't got enough magnets to put in here. So I just want to show you what happens when we get to this point here. It'll jump suddenly to the end like you just saw there, but once it gets to the end, if it doesn't stick to the wall, which is another problem, which is once it gets to the end, you'll notice that the ferrite is not bending, right? We can actually move it out. When we get to a certain point, we should be able to move it out, right? We can come out without it bending, right? But if I try to push it back, it will bend. You see, it's really a lot of force there. There's a lot of force on that point there. As you can see, it's bending because it's entry. So it basically, when you're coming in, you have a massive amount of force pulling it in, right, and not much leaving. So because that magnet's at the bottom down there, it's allowing us to leave more easily. So ferrite magnet coming in, it's pulling it in really strong, and then we can leave without it pulling us back. So there's greater force on the entry point than there is on the exit, and that's because what we've got now is we have 3 similar poles on this side, and that magnet at the bottom pointing up is biasing this ferrite with the same pole, which is rejecting the poles on this side, on the outside of these magnets. So the pole that's coming up from the bottom is going through the ferrite, and so we effectively have 3 like poles, and they don't like each other. When I say like, I mean 3 identical or similar polarities of, say, north, north, north. And because they don't like being pushed together, they're going to reject. So anyway, this is my explanation to try to show you how we can use that to, as you can say, it pulls it in really strong and we can leave, right? So you get the idea. That's my explanation, and that's what I'm working on at the moment. Right, so I hope that makes sense to you. As you know, you can't put 2 south-facing magnets together because they'll reject, and you can't put 2 north-field magnets together because they'll reject. So instead of deadening the ends, instead of subtracting the end, it's better to actually boost the ends. It's actually the opposite of what you think, but don't boost the ends with just 1 magnet. You've got to use multiples. So you could effectively use a whole bunch of little magnets in a row, spaced out all the way down the wall. Coming down the wall, you could have a whole bunch of these little round magnets, all the same pole, and they would reject once you got to the end and kick out whatever it is you've been pulling through. So we could have effect like a little lot of traffic lights. So that's another way, which I haven't worked on yet because it's quite difficult to 3D print that, but that's another idea for another day. So I hope that makes sense. Right, bye for now. Shit. My freaking audio was up again. What the hell's wrong with this stupid... Ugh. Have I just been talking for 14 minutes without any audio? Streamlabs, you suck. So I was explaining that by using like-minded poles on the exit point, instead of subtracting the exit poles on this side and on this side, instead of subtracting, say, 2 north poles with a south pole, or 2 south poles with a north pole, you add extra poles. So you have north, 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 and just as when you put two north fields together, two magnets with two similar poles together, they will reject each other, and that is how we get our expulsion out of the segment. So I've been talking to myself for 14 minutes and the freaking audio was off, and I don't know why. So as I say, it's got a huge entry pole because it's actually bending my ferrite off the magnet there, look. So when I come in, let's look down on it, it's really pulling in strong. But once it gets to the point where we have three poles the same, it actually becomes easy. It's obviously sticking to the wall, but it becomes a lot easier to leave. If you see, we can actually leave without it pulling a magnet because it's got three poles through the ferrite, all in ejection mode, right? So when we're coming in, we have a huge pull there. It's so strong that it's pulling the ferrite off the magnet. That's how strong it is, right there. And on the exit point we have virtually none. So instead of subtracting the field on the exit point, which would be to use an opposite pole, as I say with the segments, so instead of having south and south subtracting north, you have more norths. So you have a stronger propulsion through the array coming out the other end. So yeah, I'm going to have to edit this video to maybe at some point and cut part of the waffle out where the audio was muted. I don't know how that happened, but this stupid Streamlabs, it's just playing games with me again. So another way of doing it would be to have traffic lights magnets all the way down the sidewall on the inside, all the way down, say like north, 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 and they're all pushing against each other, you see. And because they're all pushing against each other, any piece of metal that you try to bring across them is not going to stick to them. It's just going to fly straight past, right? So that's the solution I've been working on. Okay, thanks for watching.